Okay, some solved problems for chapter 32. We know we have an EM wave, and we know the maximum magnetic field strength, and we know the wavelength. We know which direction it's traveling. So we're asked what is the what is the frequency of this guy? Well, very simply, we know that the speed is going to be equal to the wavelength, or the frequency multiplied by the wavelength. The speed is going to be the speed of light. So the frequency of this guy is simply going to be the speed of light divided by the wavelength, or 3 times 10 to the 8th meters per second, divided by 432 times 10 to the negative 9th. And we're going to come up with the frequency being equal to 6.9 for repeating, times 10 to the 14th hertz. For part B, we're asked for the associated electric field magnitude. We know that there's a relationship between the electric field and the magnetic field, such that the electric field is going to be equal to the speed of light multiplied by the magnetic field. So we can say this is going to simply be 3 times 10 to the 8th meters per second. Again, that's the speed of light. And 1.25 times 10 to the minus 6 Tesla. And we're going to get 375 newtons per coulomb. For part C, we're asked for the expressions of the electric fields and magnetic field in terms of x and t. I've saved myself a little bit of time by kind of writing these guys up here. So what we need to do is we need to figure out what k is and what omega is. Fortunately, everything we know from mechanical waves is going to translate. K is simply going to be equal to 2 pi divided by the wavelength. So 2 pi divided by 432 times 10 to the negative 9th. And I'm going to come up with my k to be 1.45 times 10 to the 7th. And that's going to be radians per meter. And then figure out what omega is going to be. Omega is simply going to be 2 pi multiplied by the frequency, which is going to be 6 times 6, which is going to be 6.9 for repeating, times 10 to the 14th. And so I'm going to come up with 4.36 times 10 to the 15th radians per second. And now it's just a simple matter of plugging those guys in right there, as well as the electric field and then the magnetic field, and I'll save myself from writing that. Problem number 21, we have a space probe that's in some orbit around a star. So I just kind of draw my star right here. This star is going to radiate equally, uniformly in all directions, and so it's going to be sending out essentially a spherical wave. Kind of picture the surface of a sphere right here. I'm going to have the space probe right there. It's going to make this measurement of intensity, and we're looking for the average power output. Remember that the definition of intensity is going to be equal to the power divided by the surface area of the sphere. So very simply, the power is going to be equal to the intensity multiplied by the area of the sphere. Cross-sectional area of a sphere is going to be 4 pi r squared. So 4 pi r squared, and we're given what r is. So now it's a simple matter of saying we got our 5 times 10 to the 3rd. We got 4, and we have pi. Then the radius is going to be 2 times 10 to the 10th meters. Make sure you remember to square that guy. And we're going to come out with 2.5 times 10 to the 25th with the unit of watts. Okay, some solved problems for chapter 33. Here we have light coming through a beaker. It's in some unknown material, and it's going to enter some water. It's going to bend more away from the normal. And we know that water has an index of refraction of 1.33, so we kind of expect that this guy is going to be larger than 1.33 because it's bent more away from normal. Then it's going to go from the water to air. Air has an index of refraction of 1, so we expect it to kind of go off in that direction at an even larger angle. First, we're asked to solve for the index of refraction. We're going from A to B of material A, so we start with Snell's law right there. And we say the index of refraction of A has got to be equal to the index of refraction of B, which we know. multiplied by the sine of theta b divided by the sine of theta a. Now remember, keep in mind these angles are the angles away from normal. We're given theta b, we don't have theta a. We need to actually calculate that because it has to be the angle away from normal. We do 65 minus 90 and we come up with theta a to be equal to 25 degrees. So the index of refraction is simply going to be the index of refraction of water, 1.33. Sine of 48 divided by sine of 25. We're going to get the index of refraction of this guy to be 2.34, so that's kind of part A right here. Now we're looking for the angle that light makes with air. So now this is going to be our material A, and this is going to be material B. We essentially say the same thing. We're going to say sine of theta b is going to be equal to NA divided by NB multiplied by sine of theta A. So we can go ahead and say this is going to be 1.33 divided by 1 multiplied by sine of 48. Go ahead and take the arc sine of both sides. We're going to get theta b is going to be equal to 82 degrees. So a problem on using polarizers. We're going to have some initially unpolarized light. We know that has some intensity of I0. It's going to go through two polarizing filters, so we got 1 and 2. It's going to go through the first polarizing filter, and that's going to cut its intensity in half. And then it's going to go through the second one. It tells us that the angle is going to be equal to 60 degrees. So we're going to say that the intensity is going to be equal to, first we're going to lose I0 divided by 2 going through the first polarizer, and then the second polarizer is going to take off cosine squared of 60, essentially Malice's law. So we go ahead and we heck all those guys into a calculator, and we're going to say the intensity is 0.375, the initial intensity. And lastly, a little bit more practice using Snell's law. Suppose we had a glass and we couldn't actually see into it. What you're kind of looking at is you're looking at more or less just kind of the edge of the glass, but it turns out that there's actually a dime inside that glass, only you can't see it because it's transparent. And then your friend is going to fill it up with some material, and then you're going to keep your eye in the same position, and now you're going to see the dime kind of sitting in the center of the glass. So what it's asking is, what is the index of refraction right here? Well, to do that, we need to know what this angle is, and we need to know what this angle is right there. So to do that, we use the information from the first part to say, hey, look, right here we have some angle, and that's going to be the same as that angle right there. And since I don't move, I can calculate out what the angle is. So here we know the opposite side, or the adjacent side and the opposite side, and so that tells us we're going to say that the tangent of theta A is going to be equal to the opposite. It's going to be 8 centimeters divided by the adjacent, 16 centimeters. And now we know that theta A is going to be equal to 26.57 degrees. We do the same thing right here where we want to know what theta B is. We say tangent of theta B is going to be equal to the opposite side, now just 4 centimeters, and then the adjacent side, 16 centimeters. And so we get theta B to be equal to 14.04 degrees. Now it's just a simple application of Snell's law where we're looking for that guy right there. So we're going to say index of refraction for object B is going to be equal to the index of refraction of A, sine theta A, divided by sine theta B. Index of refraction of air is just going to be 1. And then we're going to have sine of theta A, so sine of 26.57. And then sine of 14.04 That's going to give us our index refraction of the material to be 1.84.